Okay, so guys, here we go. You have got your homework packets. You've got the notes page that you have in front of you, and you're going to put everything else away except for that, and then we'll be ready to go. So guys, this is the promise that I make to you. Number one, you are going to walk out of here today wildly confused. It's just, guys, I've warned you about this for the last 2 days. Guys, today what we're going to do is we are going to tear the Bohr model apart. Remember we talked about the straw man, right? We're going to tear the Bohr model apart, but we're not going to replace it. Guys, here's what we are going to do. And if you look at your notes page, this is the way this is going to roll out. So guys, the first thing we're going to do is we're going to build the Bohr model up for one last time. Then we're going to rip it apart. That's called the Heisenberg uncertainty principle. Then we're going to talk about the conceptual framework that replaces the Bohr model. And that's all about the concept of probability. Once you understand, you see how I'm following down the notes page? That's probability. Then, guys, we are going to engage in this table that is here that says Bohr and Schrödinger, which are names that you're familiar with given the history in the last test we took. So, guys, once we're done filling in that table, you should have this experience where you go, okay, I get it, the Bohr model is dead. Then, after that, guys, in about 7 to 10 minutes, we are going to fill out this outline down at the bottom. This is where you're going to start to get confused, because you're going to be like, oh my gosh, that was a lot of information. I'm the kind of student that typically can make connections and understand things, and I'm not making the connections. And guys, I'll be honest with you, first period, it drove my students nuts. Alex Cajun, who sits back here next to Robert, was like, wait a minute, so this is this, is this, is this. And I'm just like, Alex, just trust me, buddy. I love Alex. I'm like, just trust me, buddy. It's going to be, because Alex is one of those kids, like most of you are, that just wants to understand. And I'm like, just trust me. It's going to be okay. But then we were like, then how do you know if you're okay if you know you don't know? And guys, the answer is this, and you got to hear this. If you can do the homework, you're okay. So guys, when we're done with today and you're going, oh my gosh, I don't feel like I understand, I'm confused and I don't like it, guys, you just got to trust me. That's why you got your homework packet out. We're going to transition immediately into your homework. And if you can answer the questions in homework, you're okay. Then, guys, what's going to happen is this. When I see you on Tuesday, you're going to get this out. You're going to get your class notes out. And guys, these class notes are going to be the foundation for Tuesday's day. And we're going to take all this information down here in this outline, and we're going to reorganize it. And when we reorganize it, guess what's going to leap off of this page? That stuff. Because guys, all of this stuff, all of these crazy shapes, all of this nutty stuff is actually in the outline at the bottom of your page. You're just not going to know it until I see you Tuesday. So guys, do you understand the progression and how this is going to go? Okay, so guys, here's the deal. Do not write anything down that doesn't show up on this paper. You're going to see a lot of stuff on the screen that doesn't come up here. Don't write it down. Okay? So guys, with that said, here we go. So guys, in order to start this conversation, let's look forward a little bit. You may remember from the third Hank Green video that we talked about this idea of orbitals. And during that part of the video, these slides came in, the S, the P, the D, the F, and we saw the S orbitals. And we saw that they are these pretty little spheres. And then the Ds, or the Ps that are sort of like figure eights. And then the Ds that are sort of like clover leaves. And then the Fs that are all funky. And guys, this is where we're eventually going to get. But to get there, we've got to step back first. So guys, let's go back and let's talk again about the flame test lab. So guys, in the flame test lab, you got to gather these ideas together. Talk to me about the science behind the flame test lab. So guys, in lab, here's what we did. We took atoms, right? And these electrons are moving around the nucleus like planets around the sun. And what did you guys do in lab with the Bunsen burners? Added energy to the electrons. And what did they do? Jumped up into bigger, and by the way, the paper is the electron, jumped up into bigger orbitals. And what do we call these bigger orbitals? Excited states. But can they stay in these excited states? No. And when they fall back down to the ground state, they release the energy in the form of light. Good. Now, how do we know how far they fell? The color of the light. So if they go through a long fall, what color will the light be? Violet. And if it's a short fall, it will be red. Now, what did Bohr do with that information? Well, guys, by taking the light that electrons were emitting, he could measure the energy of the light. And by knowing the energy of the light, he could measure the length of the fall. And by knowing the length of the fall, he could figure out where the electrons were based upon where they fell back down to. And based upon that data, he started to develop a model for an atom that looked like a solar system, where he said these electrons are in orbits like planets around the sun, and we can make them jump up and we can make them fall down, and we understand that an atom looks like the solar system. Does all that sit okay with you, given what you learned in the last couple days? You're okay? Okay, so now, guys, we're ready to start tearing this thing apart. Because, guys, we understand that the Bohr model is not completely right. Is it completely wrong? No, but it's not completely right. And it's time now to finally build it up so we can tear it down. So guys, it goes like this. Today what we're going to do is we're going to figure out why the Bohr model's incomplete. We're going to then gather the information that we need to build a better model, but you're not going to like this. We're not going to build the new model. We are simply going to collect the building blocks, again in that outline down at the bottom, and then we'll piece it together on Tuesday. You ready to go? Here we go. So guys, Bohr model for the last time. Here's what you need to know, but you're not going to write this down. How do you know to not write this down? It's not in your notes. But guys, this is what we've got to agree upon. Bohr developed his model by studying falling electrons and the light that they release. As he did this, he was trying to describe electrons as little particles revolving around the nucleus like the sun. And so guys, this is it. This is the Bohr model of the atom, electrons moving in circular paths. Okay, now, as he was doing that, this model depends upon your ability to track and locate electrons. If you're going to describe electrons like little particles moving around the sun, you've got to know where they are and where they're going all of the time. Now, as Bohr developed this model, guys, and you don't need to write this down, but tuck this away in the back of your brain, he started to draw these models. And he said there are small orbits and there are bigger orbits. And he described the size of the orbit using the variable n. So this was the idea, and this is going to start to sound familiar. So guys, if this is the nucleus of an atom, and as we develop the Bohr model of the atom, we're placing electrons in orbits. And guys, I think you already know this. How many electrons can go in the first orbit? 2. And you're actually correct. Guys, 2 electrons can go in the first orbit. So 1 electron would make that hydrogen, 2 electrons would make that helium. So in the Bohr model of the atom, that's what helium looks like. Now guys, what if we want to make it lithium and add a 3rd electron? Can that 3rd electron go in the first orbit? No, where does it go? The 2nd orbit. And guys, how many electrons can go in the 2nd orbit? Do you know? It's actually 8. So in the 2nd orbit, which Bohr described as n equals 2, you can get 8 electrons in that orbit, and that would then make this element 10, which is neon. Is this feeling familiar? Okay, So guys, this was how Bohr approached the atom. And so he's studying electrons like little particles, he's exciting them, they're falling, the light, all the colors, and he's putting together this model that says that there are orbits that can hold electrons, they have capacities, and as they get bigger, you can put more electrons in them, and they just line up as shells. All that okay? Because guys, here's what happened. In about 1913, as Bohr is developing this model, and I tell you what, guys, this was going great. Everybody wanted to work with Bohr because Bohr was doing this amazing science. We finally figured out that the plum pudding model was wrong, that these electrons are lined up in orbits. Bohr was a chemistry rock star. He's publishing papers, he's talking about these orbits. It makes great sense because it looks like a solar system. Everything's fitting together. And then, guys, in 1913, it started to get ugly for Bohr. Here's what happened. Bohr is exciting electrons and they're falling down, and he's measuring energies and he's figuring out these orbits. And then, guys, all of a sudden his data just got crazy. And he's gathering this data and he's doing calculations and he's like, oh nuts, this doesn't make sense anymore. This model that I thought made so much sense, my data is no longer making sense. So guys, what do good scientists do when they're collecting data that they can't make sense of? What do? What would you do? If you were in lab and you were collecting data and the data didn't make any sense at all, start over, right? And that's what Bohr did. He started over, he cleaned all the optics on his prisms, he made sure that everything was calibrated, he made sure that these things were in vacuums so there weren't any contaminants. He cleaned everything out, he ran the experiments again, and he got the same wacky data. So then what do you do next? Guys, what do you do now as a scientist if you're still collecting data you can't make sense of? What do? Show it to your friends. And guys, that's what Bohr did. He published a paper and he said, hey, smart chemistry people, I'm doing this experiment. This is the data that I'm collecting and I can't make heads or tails of it. I don't understand what this data is telling me. I've already ran the experiment multiple times. I'm getting the same results. I don't understand. Somebody help me figure it out. And guess who read his paper? A guy named Heisenberg. It's in your notes. That means you need to write it down. Guys, here's what happened. Heisenberg read Bohr's data. And guys, Heisenberg was a much better mathematician than Bohr was. And so Heisenberg took Bohr's data. And it was actually, he's quoted as saying this. This is a loose quote, but something basically like this. He said, after digging into Bohr's data, it was so messed up, not his words, that it was if adding 2 plus 3 and 3 plus 2 gave different results. There was something so fundamentally weird about Bohr's data that even one of the best mathematicians of the day, Heisenberg, couldn't make sense of it. And so guys, Heisenberg locked himself away in this seaside, literally, in a seaside house in Europe, and he just sat there and mulled over Bohr's data. And one day, this light just went on. And Heisenberg was like, oh my gosh. The problem isn't the data. The problem is we don't understand electrons. Now guys, pause and think about this. How did Bohr describe an electron? Bohr described an electron as if it was a particle moving around the nucleus in these paths. But in order to understand electrons like that, you've got to know where they are and you've got to know where they're going. And as Heisenberg began to tear apart Bohr's data, Heisenberg was like, oh my gosh, the problem here is that the electron isn't a particle. What is it? a wave. But Heisenberg didn't know that. He said, this electron isn't a particle. And because it's not a particle, it's impossible to know where it is and where it's going, because you can't figure out where something is and something's going if it isn't a thing that you can track. And guys, he said it like this. He called it his uncertainty principle. And what does it mean to be uncertain? Not quite sure. And guys, that's what Heisenberg said. He said, when you study electrons, we can never be quite sure where they are and where they're going. So he said it like this, and this is what you want to write down. He said, we can't know exactly where an electron is and where it's going. But he realized this. He realized that the problem was not Bohr's experiments. Bohr's experiments were good. The problem was this. The problem is there's something fundamentally unusual about electrons that won't allow us to study them this way. Now guys, realize Schrodinger hasn't come into this yet, so we don't know about waves. What we do know right now is electrons aren't particles. And Heisenberg proved it. Bohr is trying to treat electrons like particles. His data starts to fall apart. Heisenberg begins to analyze his data, and Heisenberg has this aha moment where he goes, whoa, wait a minute. The problem isn't the data. The problem is our understanding of electrons. We can never know where an electron is and where it's going, his uncertainty principle. And the problem isn't Bohr's data. The problem is, fundamentally, electrons will not allow us to study them as particles because they're not particles. And guys, that was it. 1913 was a very, very dark year in subatomic research. Here's Bohr having all of this wild success, treating electrons like planets around the sun. It gets weird. Heisenberg comes in and says, not only is it weird, it's broken. And everyone went, oh nuts. If this doesn't work, we're stuck because we don't have anything better. You understand the progression? Questions? You okay? So how would you summarize this then briefly? So what was Bohr doing with electrons? Studying them as particles. And in order to understand them as particles, you've got to know where they are and where they're going. That started to fall apart. And what did Heisenberg come along and say? You can't study them that way. You can never know where they are or where they're going, his uncertainty principle. But we didn't know why, and it fell apart. So guys, that's where we are then in about 1913. Heisenberg rips Bohr's approach apart. They've got nothing to replace it, and we're stuck. Y'all caught up with me in your notes and historically? So guys, who saves the day? Schrodinger. Yeah, Schrodinger comes along, dun, da, da, and he saves the day. Now guys, listen to this carefully. What's the next word in your notes? Probability. Now listen, here's what Schrodinger did. This was his reasoning. He said, okay, I get it. Heisenberg's right. Heisenberg just told the world that we can't study electrons like little particles, and we know that because the data's breaking down when we try, so we now know that electrons can't be studied as particles. But now guys, watch. The idea is this. Remember, in order to study an electron like a particle, you need to know where it is and where it's going. And Schrodinger said this. He said, okay, if Heisenberg's right, and if I cannot tell where this electron is and where it's going all of the time, listen carefully, what if I could probably know where the electrons are most of the time? Do you see the difference? See, Bohr is trying to figure out exactly where they are all the time, and it turns out electrons can't be treated that way. Heisenberg said so. So Schrodinger comes along and he says, let's just figure out where they will probably be. That's the word in your notes, right? Let's figure out where they will probably be most of the time. And he came up with this idea of probability. So guys, what is probability? Well, it is the ability to know where the electron is most of the time. And by the way, guys, if you want to make the connection, why is it we can only tell where the electron is most of the time? Because they're not particles, they're waves. And you can't tell where a wave is all of the time. You can just tell where it probably will be most of the time. That was Schrodinger's big idea that came along later. So Schrodinger is going, okay, let's stop trying to figure out where this electron is all the time. Let's figure out where this electron is most of the time. And guys, what he did is he started to envision electrons. Don't draw this. He started to envision electrons like this. So guys, let me zoom into this and let's explain what you're looking at. So, what does this picture represent? Well, first of all, what is the heavy dot in the middle? The nucleus. So what do all the little blue dots represent? Not electrons. One electron. And where it will probably be. Now guys, if this doesn't make sense, check this out. So let's do this. Okay. All right. Here we go. So, guys, let's think about it this way. So we're gonna use. You don't need to move anything, Jared. Well, this isn't yours, right? Oh, we'll leave it there. Okay. So, guys, here's the idea. Imagine that Jared's desktop is a piece of film. Like, I know everybody's digital now, but photographic film. And imagine that we can take a light and we can shine. This doesn't mess with your headaches, does it? Okay. So guys, imagine that we can take this light and we can flash this light on the film. But then imagine that we can take, ready, an electron and put this electron between the light and the film. And if this electron is not moving, you can maybe see that it's casting a shadow on the table, on the film. Now guys, if we were to allow this to go on for a period of time, and then if we went and developed the film, what would we see on the film? A dot. Does that make sense? Okay, now guys, imagine this. Imagine that the Bohr model of the atom was correct, and that this electron was actually in a circular orbit around the nucleus. And so now as this light flashes, it's going dot, 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 dot. That's annoying. And it's making a lot of dots. Now guys, if we were to develop the film, what would we see on the film? A circle, a ring. But guys, it turns out that is not what the electron is doing. So what is the electron doing? Well, it's here. And then it disappears and it's over here. And now it's there and now it's gone and it's here. And then it's in all places at once. Remember all that crazy stuff? And it's moving and it's winging and it's zooming and it's doing this. And I promise I won't hit you. And it's going crazy and it's going all over the place. And if we could then develop that film, what would we see? Well, guys, would you agree that we would see that? Do you see what I'm saying? So guys, what do those dots represent? One electron moving through space over time. And that electron is moving randomly and it's disappearing and reappearing and jumping all over the place. And eventually over time, we would get a picture like this where we can see that there are places that the electron tends to be and places where the electron probably won't be. You get the idea? But now guys, imagine this. Imagine if we let this happen for like a day and it was just going and going and going and going and going and going, and we allowed this to go on for a really long period of time. Guys, eventually, would you agree that it would start to look like this. Do you see the connection? That if we could get all of these dots to fill in, eventually it would start to look like this. And guys, here's the thing that's crazy. This is the way that Schrodinger envisioned electrons. He said, and check this out, he said electrons are not these little points in space moving around the nucleus like planets. Electrons behave as clouds. Electrons behave as clouds, and these clouds are solids because the electrons within them are moving quickly and randomly throughout these spaces. Now, hold on. How can that be? So, guys, is an electron actually this big? No. But guess what? Electrons behave as if they're that big. So if you could see what the electrons are doing around the nucleus of the atom, they are not in paths like planets. They behave like these big solid clouds around the nucleus. No. But guys, how can that be? How can an electron behave as if it's a big solid if it's just a little point in space? Well, guys, I would propose to you that that idea is actually not that weird at all. Check this out. Just a minute, Ben. So, guys, the idea is this. Here's what we're saying. We're saying that Schrodinger completely reconceptualized the electron. And he said that electrons are not points like planets around the sun. They are like clouds. And these clouds behave as if they're solids, even though they're made of single electrons. And you're going, give me a break. How can a single point behave as if it's a big cloud? Well, guys, I would propose to you that it's really not that crazy of an idea. And you've seen things like this. So, guys, take, for example, this fan. This is going to be our atom. And if this is our atom, what's that? The nucleus. And what are the fan blades? The electrons. Now, guys, I'm going to prove to you that there is space between the electrons. I'm not very good at this, so be patient. But guys, there is so much space. Oh, that was good. There's so much space between these electrons that I can shoot rubber bands right through the spaces between the electrons. So are you convinced there's space between the electrons? But guys, check this out. Is there still space between the electrons? But doesn't it start to look like a cloud? Do you see the connection? Guys, this physically starts to look like a cloud, but it doesn't behave like a cloud. Guess what it behaves like? A solid. And I can no longer shoot rubber bands through the fan blades. Every now and then it will. But guys, I can no longer, oh, that one did. Guys, I can no longer shoot rubber bands through the fan blades because these fan blades actually because these fan blades, it never works. I know. These fan blades no longer behave as if they're spaces simply because the blades are moving. And guys, electrons are the same way. As these electrons move randomly and rapidly around the nucleus, they behave as if they're these big solids, even though we know from experience the space is still there. Now, guys, if you don't believe me that the space is still there, allow me to show you that the spaces are still there. See them? Guys, look, you can see the space. It's right there. Oh, no. Hold on. Wait, the space is right out. No. Wait, it's still there. I know it's still there. It's right there. No. Guys, But look, doesn't it look like there's space? But it doesn't behave like there's space, right? And electrons are the same way. They are points that behave like clouds. And those clouds behave like they're solids because the electrons are moving. But guys, that's what makes us solid. Remember, atoms are 99.99% empty space. Remember Lavelle Edwards Stadium with a marble in the middle? How can something that is as empty as Lavelle Edwards Stadium with a marble in the middle, how can that make us up when we know we're solid? And the answer is because those electrons in the cheap seats behave as if they occupy the entire stadium as clouds because they're moving. Okay, so now some of you are wanting to know, how does this work? So, what's happening is this. The fan is spinning and the strobe light is flashing. And I can adjust the speed at which the strobe light flashes. And that's what I'm doing with this knob. And if I can get the strobe light to flash at exactly the same speed that the fan is spinning, every time the strobe light flashes, the fan has gone through one revolution. And so the light is illuminating the blade only when it's returned back to the position it was in before. Now guys, you ready for this? For those of you that are music people, here's one, here's two, here's three, and here is four harmonics. So now guys, that blade is being illuminated 4 times per revolution. But the idea is the same, and that's what harmonics are. I don't think I can get 5. Oh, was that one there? No. Nope, can't get there. But we were close. So guys, you like the cloud idea? Okay, because guys, the deal is, this isn't just an idea. This is the way nature works. This is why we are solid and our atoms are mostly empty space. The reason that we're solid is because those electrons in our atoms behave like clouds, just like the fan blades. Ben, you've been patient. Go ahead.
Okay, it's like the electrons are moving so stinking fast that no matter where you poke or prod, it's there.
Yeah, and did you hear what Ben said? Let's go with that, and then I'm going to tell you what's really happening, because you're not going to like it. So Ben said the electron is moving so stinking fast that no matter where you poke your finger, it's there. Does that make sense? Yeah. It gets even worse than that. So guys, this is off the record. Please don't tell anybody I told you about this. This is our little secret. It gets even worse, because what actually happens is this. Is an electron a wave? Yes. Is it a particle? Yes. It's both. And this is the way that it works. And let's use the word poke it. Before you poke it, that electron is a wave that occupies this cloud-like shape. When you poke it, the electron becomes a particle and shows up exactly where you poked it. So electrons are waves until we try to study them by poking them. How do we poke them? Well, we poke them with energy, we poke them, anyway. But when we poke them, they then surrender their wave properties, take on particle properties, and exist at the place where we poked them. Kind of. But I like your description better. But because remember that when electrons move, they really aren't. They're appearing and disappearing, and they're here and they're there and they're back and they're forth. And when you poke, it goes, boop, there I am. Yeah. Yes, exactly, Ben. That's exactly right. Go ahead. Just a second. Go ahead.
Could it just be that? Okay, so like if you were trying to like poke your fingers through the fan blades,
Which I did and hurt myself. Yeah.
but like.
Yeah.
There is a space in between the fan blades, so there is empty space in between, like where this electron exists.
Right.
But sorry, like if you could like stick your finger in and out quick enough,
Yeah.
then you wouldn't get hit.
And And isn't that what Rutherford did with alpha particles? Because remember, Rutherford shot, right, and that's the difference. And not only was it fast enough, they were so massive that when they did hit electrons, they just blew the electron out of the atom. So, but you're right. In the same way that there's empty space between the fan blades, there's empty space in atoms. And it's not even close. The amount of empty space in the atom is like the empty space in Lavelle Edwards Stadium with a marble in the middle. Beautiful. Yes, that's the idea. That's you and Ben are singing the same song, and that's exactly it. Go. Actually, just a second. Go ahead.
So, if they just like kind of teleport around randomly, why do they like kind of congregate in the middle? That's a okay. Beautiful. So, I like teleport. So, if they're just sort of jumping around, teleporting, why do they congregate in the middle? And maybe the follow-up question is, why do they congregate in circular patterns around the middle? So first of all, why do they congregate around the middle? Because they're negative and the nucleus is positive and they're attracted. Why would they ever go to the outside? Right, and so why, and the reason is because it's truly random. It's a chaotic system, and at some points they'll be further away, and at sometimes they'll be closer, but they want to be closer more often, and the reason is because it takes less energy. It's less energy is involved in being close than there is in being far away. And we learned that in the flame test lab. If we add energy to the electron, it'll move away, and when it comes back down, it releases that energy as light. So it's easier for it to be close, but on average, sometimes it could be over here too. Is that okay? Go ahead. You know what? It gets even worse. I've seen the math, and it's crazy. So imagine that you lean up against a door. Why don't I go through the door? Because my clouds are lining up with these clouds, and because they're behaving as solids, the clouds line up, and this is solid to solid. But statistically, there's a chance that when I lean up against this door, my clouds will be out of sync with all of these clouds, and I'll go right through the door. But in order for that to happen, you said one atom, right? But it could be more than one atom. And on average, there is the very small possibility that I can lean up against this door and go straight through, because my clouds and these atoms' clouds lined up in just such a way that they didn't interfere with each other, and you go straight through. But understand the chances of that would have to be the chances of each individual atom lining up times the number of atoms there are, which basically means it's zero. But it's not really zero. In theory, it could happen. It just doesn't because the chances are so small. I know. Go ahead.
So, like, if ever, like, that did happen,
Yep.
like, even this small.
Yeah. Yeah, right.
If you, like, if they, like, interfered with each other again, as you're, like, halfway through the door, does the door materialize inside of you? Or, like...
What if I said yes? Would you believe me?
Yeah.
Yes. That's exactly what happens.
You just, like, there's, like, too much...
No, but understand, there's no way to answer the question, because the thing that you're talking about statistically could never happen, and because it's never happened, we don't know what would happen. But I'm going to say yes because that sounds cooler. So yes, you would be married together with the door at the atomic level. I just made that up. I don't know. Go ahead, Mark.
So in a hydrogen atom, there's a one factor that makes an F.
It actually is.
Nucleus. So that's just like technically could that electron like be like way outside of
Oh yeah, so it doesn't just have to be hydrogen. So right now, there are electrons from my atoms inside of you. It's not very many, and it's not very likely, but understand these clouds are the clouds that describe the highest probability. Well, 90%'s not an actual, I know it says that, but it's just most of the time. But that's not a firm number. But understand that there isn't an asymptote. It doesn't go to zero. So our electrons, in theory, could be anywhere, including... Well, the two aren't related, but both are true. Right. Right. So and understand, and this is the problem. And this is why Einstein hated Schrodinger. So guys, this is interesting if you want to hear this. So all of this is based on probability, right? Electrons appearing and disappearing and all this stuff. Einstein hated this stuff. He's famously quoted, and you guys understand the rule, right? If you ever don't know who said something, attribute it to Einstein. Right. This one Einstein actually said. When Einstein looked at Schrodinger's ideas of probability, he said, I hate this because God doesn't play dice. Dice is probability. Einstein's like, no, electrons are particles, and we can study them. The problem is we're just not good enough at it yet. Einstein hated Schrodinger because Schrodinger was saying electrons are unstudyable because they're waves. Einstein was saying, sorry, I can't live in a world of probability. I believe that there are answers, and therefore this can't be right. And so that whole idea of electrons being in two places at one time, it's not just you that has a hard time wrapping their head around. So did Einstein. Einstein hated those ideas. Turns out he was wrong, but he hated them because it just doesn't make sense to us. The world that we live in, you're there, I'm here, we're not in two places at once. But at the subatomic level, it happens, and we've never experienced it. You're right. And so at some point, we do get to the point where the electron is so far away that it's no longer bound to the atom. It doesn't mean that it can't come back. But there is sort of like an outer limit where practically it's been removed and becomes an ion. Exactly. Right. Exactly. Yeah, but we'll deal with that in the next unit. Go ahead, Ben. Just a second.
Is it possible that like someday in the future we'll have fast enough where we can actually predict precisely where electrons are going?
And the answer is no. But so Ben is saying, will we ever have computers that are fast enough that we can predict where they are? And that was Heisenberg and Bohr. Remember, so Bohr was generating this data that made no sense, and Heisenberg said, it's not the data that's wrong, it's the model that's wrong. So this idea of tracking electrons is not limited by our computing abilities, it's limited by the fact that electrons are untrackable. There's another famous, he's actually an Iranian physicist named Jim Akalili, and he is actually famous for saying there are some questions that the universe simply will not allow us to ask. And that's one of them. Where is an electron? It's a question that the universe just won't let us ask because it's unknowable. It's not limited by our, it's a question that doesn't make sense given the behavior of electrons. Last one, and then we're going to go on.
So if the electron goes exactly where you touch, why is there
Yeah, because realize that in a gas, it's not the electrons that are spread out, it's the atoms that are spread out. So when you go like this through a gas, in many instances, you're nowhere near any atoms because they're all spread around. So it's not like you're interacting with the electrons in there. You're not touching atoms at all. And so inside a gas, the atoms are spread out and not just the electrons. And that's what causes things to be gases. Last one.
So like, if an electron is in two places,
Yes.
wouldn't it just be like two separate identical electrons?
And it's not. It's literally the same electron in two places. How can that be? It makes no sense to us. And it does, in this world, it doesn't make sense. But in the subatomic world, it happens all the time. It's crazy, right? I know. All right, so guys, here we go. Underneath probability, write this down. So this is what you need to know about this idea of probability. Probability treats electrons as if they occupy the whole space, rather than being points on a path. And guys, these spaces have names. They are called electron clouds or orbitals. And when you're done writing that down, you're done with the notes relative to probability. So guys, as if this couldn't get any crazier, check this out. You ready? Can I go on? So it turns out that not only are these orbitals more like clouds than they are like orbits, but many of them aren't even circular. So remember when we did neon, and we said 2 electrons in the first ring and 8 electrons in the second orbit, and that was neon? Guys, check this out. That was neon in the Bohr model, and that's not right. You ready? This is what neon actually looks like. This is a neon atom. Guys, let me explain to you ever so briefly what it is you're looking at. So guys, you can see the clouds, right? Well, here, hold on. That's weird. Why did that work, but the other didn't? Let me try this again. So guys, here, for some reason my board's not connected. This is bad because it's not going to let me write. Just one second. Go look for it again. Oh, there it goes. Okay, so guys, here is one of those clouds. It is a small spherical cloud. Here is another cloud. It is a larger spherical cloud. But guys, there's actually 3 more clouds in this picture, and they are not spherical. One of them is figure 8 shaped, and it's oriented up and down. Another one is figure 8 shaped, and it is oriented left and right. And then the third one is figure 8 shaped, and it is oriented in and out of the board. And what we end up with then is 2, 4, 6, 8, 10 electrons. And guys, this is actually what a neon atom looks like. It's not orbits, it's orbitals. And these orbitals, these clouds that behave like solids, which is where the electrons actually are, in neon looks like this. This is a neon atom. Go ahead. Yes. What determines the shape? And we're going to talk all about that on Tuesday, because it gets even worse, because some of them aren't spheres or figure eights, they're like clover leaves. And others of them look like these, well, they look like this. So we've got spheres, and we've got figure eights, and we've got clover leaves, and we've got crazy, crazy things. And what determines their shapes? And we're going to talk about that on Tuesday. But these are those. Those are the orbitals. And those are the spaces these electrons actually occupy. Go ahead, Anna.
So, you were saying earlier that, like, it's correct that, like, the first orbital
Has two, yes.
the bigger one. So, like, these ones are different shapes, and, like, we can tell, like, they're different types of orbitals.
Yes.
That makes sense that they have two. But what about the two spheres?
Yeah, check this out. So here are the first two electrons in a small space. Now, in this space right here, there are actually 8 electrons. 2 of them are in a sphere, and then 2 of them are in here, 2 of them are in here, 2 of them are in here, for a total of 8. So there are 8 electrons in there. It's just 2 are in a sphere, and then the 6 of them are in the figure 8s, but it still adds up to 8.
So does every atom have, like, the first orbital is, like, a small little cloud?
And it builds out from there. That's what we're doing Tuesday. Go ahead, Mark.
Do all the noble gases end in a sphere?
No. All the noble gases actually end in the figure 8s.
Wait, so which ones end in a sphere? So like, so it goes to small spheres and the bigger spheres, then it goes into
I told you, you guys were going to hate this. Because I know you love it, but you're going to hate it, because guess what I'm going to say now? We're going to do it Tuesday. No. Guys, hold on. Here's the problem. I know you, I told you, you guys are all Alex Cajunses, right? You're going, come on, you can't do this to me. Guess what? I'm going to do this to you. Guys, no, we are now, all of these questions that you guys, this is just going to make Tuesday so much better for you. It's going to be like Christmas, and you guys are all the kids that want to open your gifts early. I'm going to make you wait for Santa. I know you hate me, right? I'm okay with that. All right, so guys, let's do this. No. So now what I'm going to do is I'm going to distract you just like your parents do by loading you up with sugar so you forget Christmas is coming at all. So, guys, here we go. We are now going to put the Bohr model to rest for good. You ready? What's wrong with the Bohr model? Not everything, but enough that we needed to move past it. So guys, why? Well, the problem with the Bohr model fundamentally is it tried to treat electrons like particles. And they aren't. What are they? They're waves. See, guys, because the problem is when you treat an electron like a particle, you end up with a model that's just way too simple. And electrons aren't simple. Guys, instead, as we talk about electrons, we need to appreciate the fact that these are complex. But guys, in the 1910s, we thought simple was right because it was based on a solar system model. And it all just seemed to fit together so beautifully. But it turns out it's not solar systems, it's electron clouds. See, the problem is when you talk about solar systems, you're talking about orbits. But guys, the electrons don't exist in orbits, they exist in orbitals. See, because when you think about orbits, you're thinking about a path. But when you think about orbitals, what other P word are you thinking of? Probabilities. Now, guys, when you think about these complex orbital probability models, you need to take into account the complexity. So here's what happened. In the Bohr model of the atom, remember this? He said the size of the orbit is given by n. Well, guys, it turns out he was right. These, not orbits, but orbitals do have different sizes. But it doesn't stop there. They also have interesting shapes. And they also have crazy orientations. And Schrödinger added additional variables to account for the shapes and the orientations. And he added 3 more variables, L, M, and S. So guys, do this with me. Go down to your outlines. Ready? Write this in with me. See where it says principal quantum number? That's n. Put n in the parentheses. Now guys, the sublevel quantum number, that is L. That tells us the shape. Then, guys, the orbital quantum number is m. That tells us the orientation. And then the spin quantum number is s, and we'll talk more about that in a minute. So, guys, this is the point where this is, I promise you, this is going to kill you guys. More than any other class that I work with this year, you're going to hate this. Because, guys, what we're going to do now is we're going to flesh out this outline, and I'm going to give you all the pieces and parts that are this. And I'm not going to help you put it together till Tuesday. That makes me chemistry Santa Claus. Ho, ho. But I am growing the beard. Slowly. All right, guys, here we go. Now, this is, so every fall, the last time I shave is fall break, and then I grow a beard for skiing, because there's nothing more fun than a powder day when the snow gets caught in your beard. And then my last day of skiing, I shave it off for cycling season. So that's kind of how we roll. Oh, it's the best. Oh, yeah, I love it. All right, so guys, principal quantum number n. Here's what you need to know. Guys, n, just fill in the blanks, tells you the size of the energy level or the cloud. Now, when we talk about the sizes of these clouds, on our periodic table, there are only 7. These values only range from 1 to 7. Now, how many electrons can go in these sizes of clouds? Well, you believe that it's 2, and then 8, and then 8, and then 8. And that's not right. Guys, the capacity is given by what is called the 2n squared rule. And if you'd like to write this down with me, here's how this works. Oh, golly. Not in blue. So, guys, there are 7. Feel free to do this with me. There are 7 energy levels. How many electrons can go in energy level 1? Well, you already know it's 2. How many can go in energy level 2? Well, you already know it's 8. How many can go in energy level 3? It's not 8. Guys, plug 3 in for n. What is 3 squared? 9. Double it? 18. How many go in energy level 4? 32. 16 times 2. What about energy level 5? 5 squared is 25. Double it? 50. How many can go in 6? 72. How many go in 7? 49. 98. Guys, that is how many electrons can go in an energy level. Now, what is different about these electrons in the different energy levels? Well, here's what you need to know. As n increases, 3 things go up. First of all, the size goes up. Also, the energy goes up. But you already had that. You did the test lab. Add energy to an electron, it jumps out. Point it back down, it releases energy. And guys, you just learned that the capacity goes up. That's the 2n squared rule. Okay. But guys, this is the thing that's interesting. This is all called our model of the atom. Bohr came up with all of this, and he thought it was complete. Schrodinger proved that it wasn't. Well, actually, Heisenberg proved that it wasn't. Schrodinger fixed it. So what did Schrodinger do to fix it? He added more variables. So guys, Schrodinger took the energy levels and broke them down into sublevels. So, how many sublevels can be in an energy level? The answer is n. The number of sublevels in an energy level is n. That'll make more sense in just a minute. Now, what are the sublevels? They have names. Their names are letters. S, P, D, and F. So the letter S actually stands for simple. So it goes simple, primary, diffuse, and fundamental. That's what the letters stand for. You don't need to know that. But guys, this sounds familiar, right? S, P, D, and F? That's these. The S, the P, the D, and the F. No, he just threw that in because he thought it was funny. Okay, so guys, what do we do with this then? Guys, watch my fingers, and this is going to make sense, but you need to know this. First energy level contains how many sublevels? 1. That's what it means that the number of sublevels in an energy level is n. First energy level has 1 sublevel, the second has 2, the third has 3, the fourth has 4, fifth 5, 6, 6, 7, 7. Okay, now do this. The first energy level has 1 sublevel. It's an S. The second energy level has 2, S and P. The third energy level has 3. Want to guess what they are? S, P, D. The fourth has 4, S, P, D, F. The fifth has 5, S, P, D, F, G. But, guys, hold on. We don't have atoms in our universe that are complex enough to have a G sublevel, so we just don't worry about it. So it goes S, SP, SPD, SPDF, and then all the rest are just SPDF. Now, these sublevels don't stop there. They are broken down into orbitals. Orbitals, guys, are the clouds. And each one of these clouds can contain 2 electrons. But guys, this is a problem. These are electrons. What are their charges? Negative. Do they want to pair up? They want to repel. So guys, check this out. This is pretty cool. How is it that electrons can pair in an orbital if they're both negative and they want to repel? Here's the answer. Are electrons negative? Yes. But guess what? They're also magnetic. Guys, electrons, watch my fingers, electrons have north poles and south poles, just like the planet Earth. Now, if you have 2 electrons, and my fingers are pointing north, if you have 2 electrons and they come together north pole to north pole, they will repel. One of them flips. So guys, when 2 electrons come together and pair in an orbital, one of them will flip over, and now they line up north pole to south pole, and that attracts. Now, they're still negative, so they repel a little, so they move apart from each other in the orbital, but it does allow them to pair up in the orbital because their opposite north and south poles attract. Now, how can we tell which direction the poles are pointing? Well, guys, the Earth has a north pole and a south pole, and what does it do? It spins around the pole. So do electrons. So electrons spin around their poles. And if one of them flips over, what then happens to its spin? It's now spinning in the opposite direction. And we can actually measure which direction electrons are spinning. And when they pair up in an orbital, we see that they're spinning in opposite directions, telling us that their north poles are facing in opposite directions. Just a second. So we call this the spin number. And guys, the spin number simply represents the idea that in order for electrons to pair up in an orbital, they must have opposite magnetic poles. Now, and this I didn't put in your notes because it ran off the page, but you've got one more line in your notes. So guys, an up electron we draw like this, and a down electron we draw like this.